some of them if you want. Any that aren't of a graphical nature. Usually with an attached file, it'll take a minute or two for them to get to me.
Okay, so there's, oh wait, those are graphs. Well, the other ones have tables, and then the other ones need to be graphed.
Okay. Why don't we start with the ones that need to be graphed?
Okay.
I'll do that. I'll end up doing that the same way, whether I'm looking at your thing or not.
Okay. So it says graph the function, describe the domain and range, and compare the graph to the graph of y equals the square root of x.
Okay.
Okay, so the first equation is y equals square root of x minus 6.
With the minus 6 inside the radical? Or outside?
No, outside of it.
Okay. Let's start with graphing the parent function. You know what this looks like? Where does it start? This is actually one of the few graphs that starts with a closed dot right in the middle of the coordinate system, because both x and y have to both be positive. So that's what y equals square root of x looks like. So what's the y equals square root of x minus 6? What's the consequences of this number on the end of the function?
Isn't the minus of negative 6?
It does what?
Isn't the y negative 6?
What's the transformation? In other words, what happens to this graph y equals square root of x? Does it go right? Does it go left? Does it go up? Does it go down?
It goes down.
Okay. Okay. That's what I was trying to get. In other words, it looks like this. Okay. And here, let's label that. And its domain?
All real numbers.
Can it be negative?
Yeah.
No, not really. Notice that x has to be 0 or positive, because you can't take the square root of a negative number. It's not defined. It's one of those things like dividing by 0. So the domain is x greater than or equal to 0. On the parent function, this one up here, what's the range?
Y is greater than or equal to negative 6.
Well, that's on the function that we're working with, yes. On the parent function, the range is y is greater than or equal to 0. But in terms of the range of this one, yes, you hit it right on the head. Okay? What's another one?
Oh, did you get the email? My dad said that he sent it to you.
Yes, I did get it. Here, let me open it up.
Okay, there's 2 of them. I think the second sheet is the one we're working on right now.
Okay. Actually, it looks like there's 4 attachments. Actually, it looks like just 2. I don't know what these other two files are. I don't think they're needed. Let me just make sure I can open this by itself. Yeah. So the problem we're working on is on the second one. Okay. You want to stay on these while we're on this topic, or do you want to go to end page 1?
We can go to page 1, I guess.
Okay. These are all story problems?
I think so.
Yeah. Or word problems, really. Hold on, I'll get with you here in a second. All right. You want to start it with 1? Wow. Find the y value that makes the table represent. Did she really mean to say nonlinear function? She couldn't.
I'm not sure.
Because the only y value that we can find that makes the table make any sense at all, notice that y is 13 times x. 26 is 13 times 2. 78 is 13 times 6. So the number that has to go there has to be 13 times 4, which would be 52. However, in other words, now the table looks like this. The thing is if you graph that, that's a linear function. 2, 4, 6 for the x-axis, and 26, 52, 78. That's a straight line function. Now, the question makes sense if she meant linear and not nonlinear. If she meant nonlinear, then any number other than 52 would make it nonlinear. In other words, if I make that number there instead of at 52, then in order to graph these 3 points, I would have to have a curved line. Linear means straight line. Nonlinear means not straight line or curved. So this question doesn't really make sense if it's nonlinear. I got to think she made a typo, and especially in Algebra 1. So I'm pretty sure the answer is 52.
Oh wait, actually, could we do the second page? Because I think that one's more important since it's a study guide.
Okay, it is definitely significantly different, and I kind of agree myself that this is probably more important for you.
Okay.
I'm going to go back to this drawing here, and we'll operate off of this so I don't have to keep redrawing it. Let's see, which one we did.
Now we're on 12.
Yeah, we need 12.
Mm-hmm.
So we'll write it right here. Y equal square root of x plus 9. Where am I going to draw this, and how does it relate to the parent function, and what's its domain and what's its range?
It moves up 9.
Okay. With a closed dot starting right there. And what's its domain?
X is greater than or equal to 0.
Okay. What's its range?
Y is greater than or equal to 9.
Okay. Here. This is what we want to do, is draw this one as the dotted. There. Now I can erase them as we go.
If, like for the next one, minus 5 is under the square root sign.
Okay.
So isn't that,
So what's the consequence of that?
it moves right?
Yes, by 5 units. So I go over here to the number 5 on the x-axis, and that's what it would look like. What is its domain?
X is greater than or equal to 0.
To what?
0.
No, look at it. In other words, I switched them. So the solid line is the function that we're dealing with each problem. The dotted line is the parent function. So if you look at the solid line, that's y equals square root of x minus 5. So what are the possible x values?
5.
X greater than or equal to 5. In other words, if you look at the graph, there are no values to the left of that for x or y. It only goes to the right. So that's how you can just read your domain off of the graph once you have the graph. What's the range?
Y is greater than or equal to 0.
Okay. 14. That's x plus 4 minus 2. Okay. What's the consequences of that?
It moves down 2 and to the left 4.
Okay. So we're going to take this point right here. We're going to move it down 2 and left 4. So it's going to start right there at the coordinates minus 2, minus 4. Whoops. Minus 4, minus 2. And then we're going to draw this same curve, same shape. We're not going to change the shape of it at all. What's the domain?
X is greater than or equal to -2.
No. Which is the x-coordinate? On this xy coordinate, right. The x-coordinate is -4. So the domain would be -4. And then what's the range?
Y is greater than or equal to -2.
Okay. That's why I wanted to do that, is because I can erase a solid line with one swipe, whereas a dotted line I can't. So it makes more sense to make the dotted line the parent function. Okay, let's do 15, which is x plus 3 with a negative sign in front. First of all, here, let me write this a little better. What's the consequences of that negative sign? Because you should deal with the negative sign before you deal with anything else.
Doesn't it mean it gets skinnier?
It gets reflected about which axis?
X?
Yes. So if I were to plot y equal just the negative square root of x, it would look kind of like this. Okay? Now, what's the consequences of the plus 3 inside the radical?
It moves right 3 times?
Left. Remember, it's x minus h. And whatever h is, if h is positive, it's to the right. If h is negative, it's to the left. Well, in this case, h has to be a negative 3, because x minus a negative 3 would end up being x plus 3, which is what we have. So h is negative 3, and negative means move to the left. So if we move to the left and flip, it gives us the same thing as if we flip it first and move to the left. But that's not always the case. If there was a vertical shift going on, it would be very important to do the reflection first. So whenever we do these transformations, we always want to do the reflections first. So we'll do the reflection first, and then we'll shift 3 units to the left. So basically I'm going to go to this spot right here, which is minus 3. It looks like that. Same exact shape, only flipped over. What's the domain?
X is greater than or equal to, or less than or equal to?
No, you got it right the first time for the x.
Greater than or equal to 3? Negative 3?
And the range?
Y is greater than or equal to 0?
Is it greater than or equal to 0? We're looking at the solid line.
Oh, less than or equal to 0. Or,
Yeah, that's correct. Less than or equal to 0.
okay.
And let me erase these. That's the bad thing about that, erasing it all at one. I erased too many lines. I'm trying not to. Okay, let's look at 16. Minus 2 plus 5. So here we got 3 things going on. What's this do? What's the plus 5 do, Marina?
Makes makes it go up 3. I mean 5.
Okay. So we're looking at an up 5. We're looking at a reflection. Let's do the reflection first. I broke my own rule. We should look at that negative sign. So we're going to reflect across X. We're going to move up 5, vertical shift. And what's the minus 2 do? Or I should say, what's the consequences of the X minus 2 inside the radical?
It moves right twice.
Right 2 units. Okay, I think this may be the case where you have to do the reflection first. So we reflect this first, bringing it down to here. And then we move it right 2 units. So it would start there. And then we move it up 5 units, so it goes up here and has the same shape. See how we did that?
Yeah.
Just kind of did it one step at a time. That's right 2, up 5, reflected across the axis. Now just for the heck of it, let's see what happens if we don't do that reflection first. I think this is where it matters. Let's see, if I take this dotted thing and I move it right 2, up 5, and then reflect it, notice what happens. If I move it right 2 and up 5, it becomes this. But now if I reflect that across the x-axis, it goes all the way down to here. So you get a different thing if you do these orders of transformation in the wrong order. And where it matters is when there's a vertical shift and a horizontal reflection taking place. You have to make sure you do the reflections first. Yeah, okay. What's the... So let's see, we figured out that this solid line is the line we want. So what's the domain?
X is greater than or equal to -2.
That's a positive 2.
Oh, okay.
Okay. And y is what?
Greater than and equal to...
Oh, look at the graph. It's not greater than.
Oh, less than or equal to?
To what?
To 5.
Okay. Now, notice that if we didn't have the graph to look at, we could still figure these answers out. When we have a radical sign, we know whatever under the radical sign has to be greater than or equal to 0. So I can immediately say that x minus 2 has to be greater than or equal to 0, and that gives you your domain. Right there. So even without the graph, I can figure out the domain quite easily. The range is a little tougher to figure out. It just is. I mean, you can know that this amount, the smallest it could ever be, or the biggest it could ever be, would be 0. And so the highest y could ever be would be 5. But that's a more difficult analysis. Figuring out the range from looking at the graph is a lot easier. So if the goal is to get the domain and range, it's really easier to do to figure out the reflections and transformations or translations and do it that way. Okay, I'm going to do 17. Do you have a preference on which to do next, Marina?
No, just in order, I guess.
Okay, so 17A. What would represent a vertical translation 3 units down of that graph? What equation will do that?
Wait, what do you mean?
Well, this is the reverse of what we've been doing. In these, they give you the function, and we have to figure out what the translation is. Here, they're giving you the translation, and we have to figure out what the function is.
Okay.
So what's the
A would be the square root of x and then plus 3D?
minus
3.
minus 3. Remember, this part of it is plus. This part of it is, if it's minus, it's down. If it's plus, it's up. The part that's inside the radical is kind of the opposite, if you think about it. Negative sign means it's to the right. Positive sign means it's to the left. So what's B?
Y equals the square root of x minus 2.
Well, if I started out with this and I ask you, what does this do, what would you say?
Translates 2 units to the left.
No, you'd say it goes 2 units to the right.
Oh, okay. So it would be plus 2?
Exactly. Remember that, there's two ways to look at this. You can consider x minus h as the standard, and if h is positive, we move to the right. If h is negative, we move to the left. Or you could just look at it as, if this is negative, we move to the right. If it's positive, we move to the left. It would seem almost easier to think of it in the latter way, but the problem is with other functions, it's going to be a little different. Although not really, since x minus h is the standard on all of the functions. So, how about C?
It'd be the square root of x minus 5. It'd be y equals negative square root of x minus 5. So it'd be negative sign in front of it.
Like that?
Yeah.
Yeah. Okay. And what is D?
It'd be the square root of x plus 1. Oh, wait. Never mind. It'd be the square root of x minus 4 plus 1.
Yeah. Sometimes it's easier to work these from the back of the sentence up. Since we're writing left to right, we need to address that minus 4 first, so it actually works better if we look at this and then do this. All right. So what is the square, here, let me redraw this. What's the square root or the absolute value function look like? Looks like a V. Okay.
Okay.
And that is y equals absolute value of x. So first of all, what's the domain and range of this? Not 18, but y equal absolute value of x.
Domain is x is greater than equal, it's all real numbers.
Okay, what's the range?
Y is greater than or equal to 0.
Okay, now let's take y equal absolute value of x minus 4. How does that compare with this? What kind of translation or shift is happening?
4 units to the right.
Yeah, so it would look like this. Same exact shape, only like that. What's the domain?
All real numbers.
And the range?
Y is greater than or equal to 0.
Okay. What's the consequences of that 3, or that plus 3? What does that do? I kind of think that, I'm not quite sure if they did this intentionally, but, oh, this is a little different. This is not about translations. It actually is, it's just that they don't ask you to describe it. Well, they kind of do. They say compare the graph to this, so we do need to graph it. All right, we'll just keep proceeding. The easiest way to graph these functions is as translations or shifts. That's the easiest way to do it. In other words, if you gave me this function, 23, I wouldn't really know how to graph it. I mean, I could make up values for x, figure out what y is, and connect the dots. I could graph it that way. But the way I'm going to graph this as I'm going to figure out what the translations, what the right or left, up or down, reflection or not is doing. And that's how I'm going to graph it. So, and I think that's the best way to graph all of these if you have to graph them, by hand. So this one, what's the consequences of that 3?
It goes up 3 units.
Okay, domain.
All real numbers.
Range.
Y is greater than or equal to 0. Or 3.
3. Notice if we look at this without looking at the function, let's just look at that y equal absolute value of x plus 3. Since this part of it is always positive, that's never going to be negative, that means y has to be at least 3. It can never be less than 3. If this part is a plus 1, then y is 4, but the absolute value of x, no matter what x is never going to be less than 0. So there's no way it could be a negative number and make y less than 3. So again, you don't need the graph to figure out the range. It's just helpful in figuring out the range. All right, now we're going to get a little harder here. What's the consequences of this 2?
It translates to the left 2.
Yeah, and what's the consequences of this 2 in front of the x?
It gets wider.
It actually gets narrower.
Oh yeah, because if it's a fraction, it gets wider, right?
There you go. There you go. As long as we're talking the coefficient that's in front of the x and inside the function, then it's a horizontal shrink, basically. In other words, if I was plotting this, if I stuck a 2 in front of that, it would cause this thing to look like this. Okay?
Okay.
Which is a horizontal shrink. If let me think about this for a moment. I can actually, but I don't think they want you to do it that way. When x is equal to -1, y is equal to 0. All right. Hold on. Hold on 1 second, please, Marina. Hello? Yeah. Hi, Alex. Okay. You want to call me? Okay. Yeah. Okay. Bye-bye. Bye. Sorry about that. This one is actually a little special. This 2 right here does not actually represent 2 units to the left. It represents 1 unit to the left. And what I can do here is factor out that 2 so that I'm left with this. And now you can see that there's 2 things going on here. There's a 1 unit to the left shift, and there is a vertical stretch by a factor of 2, which actually accomplishes exactly the same thing that that horizontal shrink. It makes it a V. The difference, I'm going to turn my camera off here because my computer's shouting that I'm using too much. Ooh, it's interesting I didn't get rid of that. A vertical stretch by a factor of 2 is the same thing as a horizontal shrink by this much. The difference is that it puts the vertex in a different spot. Now, how did I know that? That the new vertex was actually there, not at -2. Well, if we go up to this and figure out what value of x makes that y equal to 0, clearly it's x equal -1, right? In other words, if you plug in -1, you get 0 inside here. If you plug in -2, that's not where y is equal to 0. So this is a little tricky. I'm kind of surprised they gave it to you. It's a much higher degree of difficulty because it requires you to factor that out before you can actually see what translation is taking place here. And it was only after I factored out the 2, now I can see it as a shift left of 1 and a vertical stretch of 2, which is what I've drawn here. And what I've drawn here fits this original function because I know that when x is minus 1, y is 0. So what's the domain?
Wait, I thought it got wider, though.
What's that?
I thought it got wider, though.
No, it gets narrower. Even if it was a horizontal shrink, it gets narrower. In other words, whether this 2 is inside the absolute value or outside has the same exact effect on this function. The difference, however, is this 2 right here is not the amount of horizontal shift. And the reason it isn't is because I haven't factored out the 2 yet. I need to factor out that 2 in order to actually find the horizontal shift, like I did. It's something we haven't done before, a problem like that, where we factored something out of the absolute value sign. All right, let's look at the next one. Now, remember what we did on the last problem? Problem 20. We need to do something similar here. In other words, I can't look at this and say that it shifts right 1 and down by 2. I can't do that because of that 1/2 sitting in front of the x.
Well, doesn't the 1/2 make it wider?
Well, yes and no. If I was looking at strictly y equal absolute value of 1/2 x, yes, I could end the discussion and say it makes it wider. But in terms of trying to figure out what kind of horizontal shift is going on here, I have to get that half outside the absolute value. I don't necessarily have to get it outside the absolute value. I can factor it like this, inside the absolute value. Let's do it that way. I think it'll become a little clearer to you. And this has to be 2. You see where that's the same thing? In fact, this is a better explanation. Rather than factoring that 1/2 outside the absolute value, because it's not totally clear that that is an allowable thing. It is, but it's not clear at this stage of algebra that you can factor numbers outside of the absolute value. They probably have not taught you that you can do that. But I don't need to do it. I merely need to get it out from in front of the x, like I've done. I've factored out that 1/2. And now notice that if I were to distribute it, I would get 1/2 x minus 1. So I haven't changed it. I still have this minus 2 sitting out there. Now I can read it. In other words, I know that it's going to go down 2, it's going to go right 2, and it's going to widen by a factor of 2. Because now the coefficient is inside the function, the absolute value, and in front of the x. So now I can legitimately say that this is a horizontal stretch. Okay? In other words, if I was just considering the 1/2, it would be like this. All right?
Okay.
if I'm considering all three, well, I'm going to go down to, there's no reflections going on, so as long as there's no reflections, I can do it in any order I want. So there's down 2, there's right 2, and so that's where my vertex is going to be, and it's going to be like this. What's the domain?
X is greater than and equal to...
Domain?
Oh, all real numbers.
What's the range?
Y is greater than or equal to 0.
No, what is this point? What's the y coordinate right there?
Oh, -2.
Yeah. Okay. Let's look at 22. Ah. 22, y is equal to -3x. Now, notice that this is different than y equals absolute value of -3x. It's even different than y equals negative absolute value of 3x. In other words, the 3 in this case here is inside the function. It's also inside the function there, but here it's in front of the function. The difference is this represents a vertical stretch. This represents a horizontal shrink. Okay? You understand the differences? They seem to be the same, but they're not always exactly the same. We discovered on parabolas that they're not exactly the same. A vertical stretch by a factor of 2 is not the same as a horizontal shrink by a factor of 2. Not in all functions, at least. In some functions, it is the same. But, so, what's the consequences of the negative sign?
It flips.
So that would be like this. And what's the consequences of the 3? It's a vertical stretch. What does that mean? It gets skinnier or fatter?
Fatter.
Skinnier. Here's how you can tell. Here, let's straighten this up because this is important. A very important general concept. If I wanted to plot that, and I didn't know whether it got fatter or skinnier, well, let's try the skinnier model and see if that works. By working, it means that if I'm comparing it to this dotted graph, which is y equal absolute value of x, well, this says that when x is 3, y is 3. It says when x is 5, y is 5. Whereas the solid graph, the skinny graph, says that when x is 3, y is 9, way up here. When x is 5, y is way up here at 15. So notice that the skinny graph works. It fits the points. It wouldn't work if I had a fatter graph. This fat graph says that the y values are a third of the other y values. In other words, notice on the fatter graph, the y values are always less than the other ones. So to get a fat graph, you need to take a fractional amount. If it was 1/3 of the absolute value of x, then I would be looking at this fatter line, not the skinnier line. So if you forget, just remember that concept. And it's true for all functions, not just the absolute value function. No matter what function you're plotting, if you're going to let y equal to a bigger multiple of it, then every point is going to be higher than it would normally be. Okay, let's look at the last one of these, which is a beauty. Minus, I assume that's a minus, right? Minus 1/3?
Yeah.
All right. What do we start with here? In terms of graphing it.
Flip it.
Okay. Then what? After that, it doesn't matter the order of the other two. So the first step is that, a flip. Okay. What's the next step? And you can do either one of them. You can do this one or this one. Let's do the -4 first. What's that do?
Makes it go to the left 4 times.
No.
To the right.
No. Remember when the number is at the very end, after the function is over? It's always an up or down movement.
Oh yeah, down 4.
So there's the down 4, and if I add the flip, now it looks like that. What's the 1/3 do? Fatter or skinnier? And what's key is the fact that this 1/3 is outside of the function. It's outside of the absolute value. In other words, this is now a vertical stretch or shrink, not a horizontal. If that 1/3 was inside in front of the x, then I could talk about it as being a horizontal stretch or shrink. But this is a vertical stretch or shrink. Fatter or skinnier?
Fatter.
Yeah. What's the range? I know you know the domain.
Y is greater than or equal to,
Hold
less
on.
than or equal to,
Okay.
-4.
Correct. Okay. All right. Why don't we wrap it up there? We got through number 23. Let's see. I don't see you until next week. When are your finals? Marina?
Can you hear me?
Yeah. When are your finals?
Okay. I think it's next week.
Okay. I've got 2 sessions scheduled with you for next week, Monday evening and Wednesday at 2:30. So those will probably be our last 2 sessions before your finals.
Probably.
Okay. All right. I will see you next week, or talk to you next week. Let's see, and I'll use whatever phone number is on those reservations.
Okay, I think use the same one as today.
Okay, for next week, for all of next week, or just Monday? Or
All of next week.
all of next week. Yeah, I see that it's all of next week is that phone number. Okay. I will talk to you next week.
Okay, thank you.
All right, bye-bye.